Tonight, we're going to ask a question you have almost certainly never thought about, and the answer is going to surprise you at every turn. The sun is spinning. Right now, at this very moment, our star is turning slowly on its axis, just as the Earth does. You probably never think about it, but that quiet, invisible spin is secretly running something so important that if it ever stopped, it would transform not just the sun, but the entire solar system in ways almost nobody would predict. So here is the question. What would actually happen if the sun stopped spinning? And I want you to notice your first instinct because it is almost certainly wrong. Most people assume that if the sun stopped spinning, something catastrophic and obvious would happen. The sun would go dark. It would stop burning. It would fall apart or its gravity would fail and the Earth would go spinning off into space. And here is the first surprise of tonight. None of that is true. If the sun stopped spinning, it would keep shining just as brightly as before. It would keep burning, keep producing light and heat without missing a beat. Its gravity would not change at all, and the Earth would continue in its orbit exactly as it does now. On the surface, you might think nothing would happen at all. But that is where the real story begins, because hidden beneath the sun's calm, shining surface is an engine, an invisible mechanism that the sun's spin secretly powers. And when that spin stops, that engine begins to die. Slowly, silently, something vital to the sun's entire character would start to fade away. The sunspots would vanish. The great eruptions, the flares and the storms would cease. The sun's magnetic personality, the violent, dynamic energy that makes it more than just a quiet ball of light, would wind down and disappear. And the effects would reach all the way across the solar system, out past the planets, changing the invisible bubble that protects us all. The sun would still shine, but it would become a fundamentally different star, a quiet, sleeping giant, stripped of the hidden force that its spin alone provides. By the end of tonight, you're going to understand the secret engine that a simple spin quietly powers, why the sun stopping would not do what you expect, and what it would actually mean for the sun, for the Earth, and for the entire solar system. This is the story of the most overlooked motion in the sky, and the profound and surprising consequences of what would happen if it ever stopped. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. Now let's begin. Before we can explore what would happen if the sun stopped spinning, we have to appreciate something we almost never stop to consider. The fact that the sun is spinning at all. It is one of those truths that is easy to forget, precisely because it is so constant and so silent. But the sun's rotation is real. It is happening right now, and understanding it is the key to everything that follows. Think about how we experience the sun. It rises in the morning, it crosses the sky, and it sets in the evening. But that motion, the daily journey of the sun across our sky, is not the sun moving. It is the Earth spinning, carrying us around so that the sun appears to move overhead. The sun's own rotation is something completely different and far less obvious. The sun, that vast ball of glowing plasma, is turning on its own axis, spinning slowly in place, just as the Earth spins on its axis to give us day and night. We simply cannot see it directly, because the sun looks like a featureless disk of light, with no obvious markings to track. And so, for most of human history, people had no idea that the sun was spinning at all. It seemed to be a perfect, unchanging, motionless orb of fire in the sky. But the sun is spinning, and it always has been since the moment it was born. In fact, spinning is one of the most fundamental things that objects in the universe do. The Earth spins, the planets spin, the galaxies spin, and the sun spins too, completing one full rotation over a period of roughly a month, turning slowly and steadily on its axis, carrying its churning surface around and around in an endless cycle. This rotation is not some minor, incidental feature of the sun. As we will discover, it is deeply connected to the sun's entire character, to the violent magnetic activity that makes our star such a dynamic and sometimes dangerous neighbor. The spin is not just a curiosity. It is, in a very real sense, one of the engines that drives the sun's behavior. And this is what makes our question tonight so fascinating. Because we so rarely think about the sun's rotation, we have almost no intuition for what it does, or for what would happen if it stopped. We take it for granted, this silent, constant spinning, without ever realizing how much depends on it. So to understand what would happen if the sun stopped spinning, we first have to understand the spin itself, how we discovered it, how strange it actually is, and where it came from in the first place. Because the sun's rotation, when you look closely, is far weirder and far more important than you might ever have guessed. And it begins with a discovery made by one of history's most famous scientists, who looked at the sun and saw something no one had understood before. Let's begin with a simple question. If the sun looks like a featureless disk of light with no visible markings, how do we even know it is spinning at all? How could anyone have discovered that this smooth, blazing orb is actually turning on its axis? The answer takes us back 4 centuries, to one of the most famous figures in the history of science, and to a discovery that changed how we understood our star. The key was something on the surface of the sun that most people assumed did not exist: sunspots. These are dark blotches that appear on the surface of the sun, regions that look darker than their surroundings. To the naked eye and to early observers, the sun seemed perfectly smooth and unblemished, a flawless sphere of light. But when astronomers began to study the sun more carefully, using early telescopes and careful observation techniques, they discovered that the sun's surface was not flawless at all. It was marked from time to time by these dark spots, and crucially, when observers tracked these sunspots over a period of days, they noticed something remarkable. The spots moved. Slowly, steadily, the dark spots drifted across the face of the sun, from one side to the other, and then disappeared around the edge, only for new ones to appear on the opposite side. This drifting motion of the sunspots was the crucial clue, because there was really only one good explanation for why spots on the sun's surface would slowly march across its face in an orderly way. The sun had to be rotating. The spots were features on the sun's surface, and as the sun turned on its axis, it carried those spots around with it, causing them to move across the visible face of the sun and then vanish around the far side, exactly as a mark on a spinning ball would appear to travel across the side facing you and then disappear around the back. One of the scientists most famously associated with this discovery was Galileo, who studied sunspots in the early 1600s and used their motion to argue that the sun was rotating. By tracking the spots as they crossed the solar disk, early astronomers could even work out roughly how long the sun took to complete one full rotation. The spinning of the sun, invisible in the smooth disk itself, was revealed by the patient tracking of the dark spots that drifted across it. This was a profound realization. It meant the sun was not a static, unchanging orb, but a rotating body, a spinning star, turning on its axis just like the Earth. And it opened the door to understanding the sun as a dynamic, active object, rather than a perfect, motionless light in the sky. The discovery that the sun spins was one of the early steps in understanding our star as a real, physical, churning body, with a surface that changes and a rotation that carries it around and around. But here is where the story takes its first strange turn. Because when astronomers looked more closely at exactly how the sun rotates, They found something that made no sense for a normal, solid object. The sun, it turned out, does not spin the way the Earth does. It spins in a way that is genuinely bizarre, a way that is only possible because the sun is not solid at all. When astronomers studied the sun's rotation carefully, tracking sunspots at different locations on its surface, they made a discovery that seemed, at first, almost impossible. The sun does not rotate all in one piece, the way a solid ball would. Different parts of the sun spin at different speeds, and this strange behavior, called differential rotation, is one of the most important and revealing facts about our star. It is unlike anything we experience with solid objects, and it holds the key to understanding the sun's hidden engine. Here is what makes it so strange. When the Earth rotates, it rotates as a single, solid body. Every part of the Earth completes one rotation in exactly the same amount of time, one day. The equator, the poles, the mid-latitudes, all of them turn together, locked into a single rotation, because the Earth is solid and its parts cannot slide past one another. This is what we expect from a spinning object. It turns all at once as one piece. But the sun does not do this. When astronomers measured how fast different parts of the sun rotate, they found that the sun's equator spins faster than its polar regions. The material near the sun's equator completes one rotation in roughly 25 days, while the material near the sun's poles takes considerably longer, around 35 days, to complete a single turn. Different latitudes on the sun are rotating at different speeds, sliding past one another as the sun turns. Think about how bizarre this is. Imagine a spinning ball where the middle turns faster than the top and bottom, where different bands of the surface rotate at different rates, endlessly sliding past each other. For a solid object, this is impossible. You cannot have the equator of a solid ball lapping its own poles. The object would tear itself apart, or simply cannot exist in that state. And yet the sun does exactly this, rotating faster at its equator than at its poles, with the different regions perpetually shearing past one another. This is differential rotation, and it is one of the defining features of the sun. The sun is not a rigid, solid body that turns all at once. It is something far stranger, a body whose different parts can and do rotate at different speeds, a spinning object unlike any solid thing in our experience. This strange, differential rotation is not just a curiosity. As we will see, it is absolutely central to the sun's magnetic activity, to the hidden engine that the sun spins secretly powers. The fact that the sun's equator laps its poles, that different regions slide past one another as the sun turns, is one of the crucial ingredients in generating the sun's powerful and ever-changing magnetic field. But before we get to why this matters so much, we have to answer an obvious question. How is this even possible? How can different parts of the sun rotate at different speeds, sliding past one another, when no solid object could ever behave this way? The answer reveals something fundamental about what the sun actually is, and why it is so different from the solid worlds we know. We have discovered that the sun rotates in a bizarre way, with its equator spinning faster than its poles, different regions sliding past one another as it turns. This is impossible for a solid object. So how does the sun do it? The answer lies in understanding what the sun actually is at its most basic level. Because the sun is not solid, it is not liquid. It is something else entirely, and that is what allows it to rotate in ways no solid world ever could. The sun is made of plasma. Plasma is often called the fourth state of matter, alongside solid, liquid, and gas. It is what you get when a gas becomes so incredibly hot that its atoms break apart, with electrons stripped away from their nuclei, leaving a churning soup of charged particles. The entire sun, from its core to its surface, is made of this superheated plasma, a vast ball of glowing, electrically charged gas at temperatures so extreme that ordinary matter cannot exist. And because the sun is made of this fluid, flowing plasma rather than solid rock, it does not have to rotate all in one piece. Different parts of the sun can flow and move independently, sliding past one another, rotating at their own speeds. The sun is, in a sense, more like a spinning ball of fluid than a spinning solid ball, and fluids can do things solids cannot, including rotating at different speeds in different regions. Think of it this way. Imagine trying to spin a solid ball versus trying to spin a ball of swirling liquid. The solid ball must turn all at once, every part locked together. But the ball of liquid can have different currents moving at different speeds, its outer layers swirling and flowing independently, some parts turning faster than others. The sun is like that ball of fluid, except it is made of superheated plasma, and it is enormous, and its flows are driven by the tremendous heat rising from its core. The plasma near the equator ends up rotating faster than the plasma near the poles, producing the differential rotation we observe. The sun can spin this way precisely because it is not solid, because it is a churning, flowing body of plasma that allows its different regions to move at their own pace. And this fluid nature of the sun is not just what allows its strange rotation. It is also what makes the sun such a dynamic, active, and sometimes violent object. Because a churning ball of electrically charged plasma, rotating differentially, with hot material rising and cooling material sinking, is the perfect setting for generating powerful magnetic fields. The very properties that allow the sun to rotate in its strange way, its fluid plasma nature and its differential rotation, are the same properties that give rise to the sun's magnetic engine. But before we explore that engine, there is one more question about the sun's spin that we need to answer. Where did it come from in the first place? Why is the sun spinning at all? The answer takes us back to the very birth of the sun and to a principle that governs spinning objects throughout the entire universe. We have established that the sun spins, and that it spins in a strange, differential way because it is made of fluid plasma. But this raises a deeper question. Why is the sun spinning at all? Where did its rotation come from? Objects do not simply start spinning for no reason. Something must have set the sun turning. And the answer takes us back to the very beginning, to the birth of the sun itself, and to one of the most elegant principles in all of physics. The sun was born from a vast cloud of gas and dust, an enormous cloud drifting in space, far larger than the sun itself. Billions of years ago, this cloud began to collapse under its own gravity, pulled inward, its material falling together toward the center, gradually forming the dense, hot ball that would become our sun. And here is the crucial point. That original cloud was not perfectly still. Like almost everything in the universe, it had some slight rotation, some gentle, overall turning motion, however small. And as the cloud collapsed, as its material fell inward and the cloud shrank down toward the center, something remarkable happened to that rotation. It sped up, dramatically. This is a consequence of a principle called the conservation of angular momentum, and you have seen it in action, even if you did not realize it. Think of a figure skater spinning on the ice. When the skater pulls their arms in close to their body, they spin faster. When they extend their arms outward, they slow down. The skater does not push off the ice to speed up. They simply pull their mass inward, and the spin accelerates on its own. This is conservation of angular momentum. When a spinning object draws its mass inward, closer to its axis, it must spin faster to compensate. And the same thing happened to the cloud that became the sun. As the vast cloud collapsed, drawing all its material inward toward the center, Its gentle initial rotation sped up more and more, just as the skater speeds up by pulling in their arms. By the time the cloud had collapsed into the dense ball of the young sun, that original slow rotation had been concentrated and accelerated into the steady spin the sun has today. So the sun's rotation is, in a very real sense, a leftover, an inheritance from the cloud it was born from. It is the original, gentle spin of that primordial cloud, concentrated and sped up by the collapse into a star. The sun spins today because the cloud that formed it was spinning, and the collapse amplified that spin into the rotation we observe. This is how virtually all stars and planets end up spinning. They inherit and concentrate the rotation of the clouds they form from. The sun's spin is a memory of its own birth, a motion set in place billions of years ago and carried faithfully ever since. And now that we understand what the sun's spin is, how strange it is, and where it came from, we can finally turn to our real question. What would happen if it stopped? And the first thing we need to establish is what would not happen, because the answers are genuinely surprising, and they overturn almost everything your intuition might suggest. Now we arrive at the heart of our question. What would happen if the sun suddenly stopped spinning? And to understand the real answer, we first have to clear away the dramatic misconceptions, the things you might instinctively expect to happen but which actually would not. Because the most common assumption, that a sun which stopped spinning would go dark and stop burning, is completely wrong, and understanding why reveals something fundamental about how the sun actually works. Here is the reassuring truth. If the sun stopped spinning, it would keep shining, just as brightly as it does now. Its light and heat would not diminish in the slightest. The sun would continue to pour out energy exactly as before, and from the earth, you would notice no change at all in the sunlight reaching us. The reason is that the sun's spin has essentially nothing to do with how it produces its energy. The sun does not shine because it is spinning. It shines because of nuclear fusion taking place deep in its core, a process completely independent of the sun's rotation. In the sun's core, under crushing pressure and unimaginable temperatures, hydrogen is being fused into helium, releasing tremendous amounts of energy. This fusion is driven by the immense gravity and heat at the sun's center, not by its rotation. Whether the sun spins quickly, slowly, or not at all, the fusion in its core would continue exactly the same, powered by gravity and temperature, not by spin. This is a crucial distinction, and it dismantles the most dramatic fear about a non-spinning sun. The engine that makes the sun shine, the nuclear furnace at its core, does not care about rotation at all. It runs on the balance between gravity pulling inward and the pressure of the hot, fusing core pushing outward, a balance that has nothing to do with how fast the sun's surface is turning. So if the sun stopped spinning, its core would keep fusing hydrogen, keep generating energy, and keep the sun shining without any interruption. The light and warmth that sustain life on Earth would continue, unchanged. The sun would not go dark, would not cool, would not stop burning. In terms of the energy it produces, a non-spinning sun would be indistinguishable from the spinning sun we know. So we can set aside the nightmare of a sun that suddenly goes out. That is not what would happen. The sun's rotation and the sun's shining are two separate things, and stopping one would not affect the other. This is the first of several surprises, and it points to an important theme. The effects of the sun stopping would not be the obvious, dramatic ones we might imagine. They would be subtler and stranger and hidden beneath the surface. The sun would keep shining, yes, but that does not mean nothing would change. It only means we have to look deeper to find what would. And before we uncover the real, hidden consequences, there are two more dramatic fears to set aside, two more things that would not happen, each of which teaches us something important about the sun. The next concerns the one force we most associate with the sun. Its gravity. We have established that a sun which stopped spinning would keep shining, its nuclear furnace undisturbed. Now let's address another dramatic fear, perhaps the most frightening one of all. The worry that if the sun stopped spinning, its gravity would somehow fail, and the Earth would go flying off into space, released from its orbit. This is a natural fear, but it too is based on a misunderstanding. The sun's gravity would not change at all if it stopped spinning, and the Earth's orbit would continue exactly as before. The reason comes down to what gravity actually depends on. The gravitational pull of any object depends on its mass and on how far away you are from it. That is all. The sun's gravity, the invisible force that holds the Earth and all the planets in their orbits, comes from the sun's enormous mass. And if the sun stopped spinning, its mass would not change in the slightest. It would still contain exactly the same amount of material, exerting exactly the same gravitational pull. The sun's rotation has nothing to do with its gravity. A spinning sun and a non-spinning sun of the same mass would pull on the Earth with precisely the same force. So the Earth would feel no change whatsoever in the sun's gravitational grip. It would continue orbiting the sun exactly as it does now, at the same distance, at the same speed, in the same stable orbit. There would be no danger of the Earth being flung off into space, because the force holding it in orbit would be completely unchanged. It is worth dwelling on why this fear feels so intuitive, even though it is wrong. We tend to associate spinning with holding things together, perhaps because we think of things like a spinning lasso, or the way spinning can create outward forces. But the sun does not hold the planets in orbit by spinning. It holds them by gravity, by the pull of its mass, and that pull exists whether the sun spins or not. The planets orbit the sun for the same reason a ball on a string circles your hand, because there is a force pulling them inward, constantly bending their path into an orbit. For the planets, that inward force is the sun's gravity, and it depends only on the sun's mass, not its rotation. Stop the sun's spin, and the gravity remains, and so do the orbits. The Earth would sail on around the sun, utterly undisturbed in its motion, just as it has for billions of years. So we can set aside this fear as well. A non-spinning sun would not release its grip on the planets. Its gravity would be exactly as strong as ever, and the solar system would keep turning, the planets tracing their same orbits around a sun that no longer spins. This is now the second dramatic consequence we have ruled out. The sun would not go dark, and its gravity would not fail. Its rotation, it turns out, is disconnected from both the energy it produces and the gravity it exerts. And this might lead you to wonder whether the sun stopping would do anything at all. Perhaps it would simply keep shining and keep holding the planets with no consequences whatsoever. But that is not the case. There is a third fear to address first, a smaller one, about the sun's very shape. And once we have set that aside too, we will finally uncover the real, profound, hidden consequence that the loss of the sun's spin would unleash. We have set aside two dramatic fears about a non-spinning sun. It would not go dark, and its gravity would not fail. Now let's address a third, subtler concern before we uncover the real consequence. You might wonder whether the sun's shape depends on its spin. After all, spinning objects tend to bulge outward at their equators. So if the sun stopped spinning, would it dramatically change shape, perhaps collapsing or transforming in some visible way? The answer, once again, is no. And understanding why reveals just how gentle the sun's spin actually is. It is true that spinning does affect the shape of an object. When something spins, the rotation creates an outward tendency at the equator, causing the object to bulge slightly around its middle and flatten slightly at its poles. This is why many rotating bodies in space are not perfect spheres, but are slightly flattened, with their equatorial diameter a bit larger than their polar diameter. The faster an object spins, the more pronounced this bulging becomes. So the sun's rotation does give it a very slight equatorial bulge. But here is the key point. The sun rotates quite slowly, taking about a month to complete a single turn, and its gravity is immensely strong, pulling all its material into a tight, spherical shape. The result is that the sun's rotational bulge is astonishingly tiny. The sun is, in fact, one of the most perfectly spherical natural objects known to exist, with its equatorial and polar diameters differing by only the smallest fraction. The bulge caused by its spin is almost immeasurably small. So what would happen to the sun's shape if it stopped spinning? It would become very slightly more spherical, its tiny equatorial bulge relaxing away as the rotation ceased. But the change would be so minuscule as to be completely imperceptible. We are talking about a shift so small that you could never see it, never notice it, never detect it without the most precise instruments. The sun is already so close to a perfect sphere that removing its gentle spin would make virtually no difference to its shape at all. There would be no dramatic collapse, no visible transformation, no sudden change in the sun's appearance. It would remain the same round, glowing orb it has always been, perhaps a vanishingly small fraction more spherical, but otherwise entirely unchanged in form. So we can add this to our list of things that would not happen. The sun would not go dark, its gravity would not fail, and its shape would barely change at all. On every obvious, dramatic level, a sun that stopped spinning would look and behave almost exactly like the sun we know. It would shine the same, pull the same, and look the same. And this might leave you thinking that the sun stopping would truly be a non-event, a change with no real consequences at all. But that conclusion would be wrong. Because everything we have discussed so far concerns the visible, surface-level properties of the sun. The real consequence of the sun stopping is hidden much deeper, in an invisible process that the sun's spin quietly powers. It is time, at last, to uncover the secret that the sun's rotation has been hiding all along, and it is a secret that governs the sun's entire character. We have ruled out all the dramatic, obvious consequences of the sun stopping. It would keep shining, keep its gravity, keep its shape. So you might reasonably ask, then what does the sun's spin actually do? If stopping it changes none of these things, why does the rotation matter at all? And here, finally, we arrive at the secret. Because the sun's spin is quietly powering something invisible, something that does not show up in the sun's brightness or its gravity or its shape, but which governs the sun's entire dynamic personality. The sun's rotation is the engine of its magnetic field. This is the hidden truth that changes everything. The sun is not just a ball of glowing plasma. It is a magnetic object, wrapped in and threaded through by powerful magnetic fields, and those magnetic fields are responsible for nearly all of the sun's active, dynamic behavior. Everything that makes the sun more than a quiet, featureless light, the dark sunspots, the violent flares, the enormous eruptions of material, the whole restless, changing character of our star, all of it flows from the sun's magnetic field. And that magnetic field, it turns out, is not a fixed, permanent feature. It has to be continuously generated and sustained by an active process going on inside the sun. That process is called the solar dynamo, and its essential ingredient, the thing that makes it work, is the sun's rotation. The spin is what drives the dynamo, and the dynamo is what creates the magnetic field, and the magnetic field is what gives the sun its entire dynamic life. Do you see the profound implication? The sun's spin does not power its light, and it does not power its gravity. but it does power its magnetism. And the sun's magnetism is the source of everything that makes it a dynamic, active, sometimes violent star. The rotation is quietly running the engine behind the sun's entire personality, an engine hidden beneath the calm surface, invisible in the sun's steady glow, but responsible for all its restless activity. When you look at a sunspot, you are seeing the work of the sun's spin. When you witness a solar flare, you are witnessing the ultimate result of the sun's rotation. The magnetic field that produces all of this is generated by the spinning of the sun, and without that spin, the whole magnetic engine would begin to shut down. This is the secret that the sun's rotation has been hiding all along. It is not the source of the sun's light or gravity, but it is the source of the sun's magnetic soul, the invisible driver of everything dynamic and active about our star. And this is why the question of what would happen if the sun stopped spinning has such a surprising and profound answer. The sun would keep shining, yes, but it would slowly lose its magnetic engine, and with it, everything that magnetism creates. To understand exactly what that means and exactly what would fade away, we first need to understand how this hidden engine, the solar dynamo, actually works. Because it is one of the most remarkable processes in all of nature, and it depends entirely on the strange, differential spin we discovered earlier. We have discovered that the sun's spin powers its magnetic field through a process called the solar dynamo. Now let's understand how this remarkable engine actually works, because it ties together everything we have learned about the sun. Its fluid plasma nature, its strange differential rotation, and its churning interior all come together to generate the powerful magnetic fields that give the sun its dynamic character. And rotation is the beating heart of the whole process. The solar dynamo requires a few key ingredients, and the sun has all of them. First, the sun is made of plasma, a fluid of electrically charged particles. When a fluid of charged particles moves, it generates magnetic fields, and it can amplify and sustain them. This is a fundamental link between motion and magnetism. Moving charges create magnetism, and in the sun, vast quantities of charged plasma are constantly in motion. Second, the sun's interior is churning with convection, with hot plasma rising up from the depths, cooling near the surface, and sinking back down in an endless, roiling circulation. This churning motion stirs the plasma and helps twist and organize the magnetic fields. And third, most crucially of all, there is the sun's rotation, and especially its differential rotation, the fact that the equator spins faster than the poles. This differential rotation is the key that winds up and amplifies the sun's magnetic field. Here is how it comes together. Imagine the sun's magnetic field as lines threading through the plasma. Because the plasma is electrically charged, the magnetic field lines are effectively locked into the plasma, dragged along wherever it flows. Now, because the sun rotates differentially, with the equator turning faster than the poles, the magnetic field lines get stretched and wound up. The faster spinning equatorial regions drag the field lines around more quickly than the slower polar regions, stretching them out and winding them tighter and tighter around the sun, like thread being wound around a spool. This winding process, driven by the differential rotation, takes the sun's magnetic field and amplifies it, concentrating it, building it up into intense, powerful bundles. Combined with the twisting action of the churning convection, this creates a self-sustaining engine that continuously generates and regenerates the sun's magnetic field, converting the energy of the sun's rotation and churning into magnetic energy. This is the solar dynamo, and rotation, especially differential rotation, is the essential ingredient that makes it run. Now you can see why the sun's spin is so vital to its magnetic field. The dynamo works by using the sun's differential rotation to wind up and amplify the magnetic field. Take away the rotation, and the central mechanism of the dynamo is gone. There is no more winding up of the field lines, no more amplification driven by the differential spin. The engine loses the very thing that powers it. Without rotation, the dynamo cannot continuously regenerate the magnetic field, and the field would begin to decay, no longer sustained by the winding action of the sun's spin. This is the crucial link between the sun's rotation and its magnetic life. The spin drives the dynamo, and the dynamo sustains the field. But this dynamo does something even more remarkable than simply generating a magnetic field. It generates a field that pulses and changes in a regular rhythm, a magnetic heartbeat that beats across the sun in a cycle lasting about 11 years. And that heartbeat, too, depends entirely on the sun's spin. The solar dynamo does not simply generate a steady, unchanging magnetic field. It produces something far more dynamic and remarkable. A magnetic field that rises and falls, builds and reverses in a regular, repeating rhythm. This is the sun's magnetic heartbeat, a cycle that plays out over roughly 11 years, and it governs the ebb and flow of all the sun's activity. And like the dynamo itself, this heartbeat depends entirely on the sun's rotation. Here is how the rhythm works. Driven by the dynamo, the sun's magnetic field goes through a cycle. Over a period of about 11 years, the magnetic field gradually builds up and becomes more and more tangled and complex, wound tighter and tighter by the differential rotation. As the field builds, the sun becomes more active, producing more and more sunspots, more flares, more eruptions. This period of maximum activity is the peak of the cycle, when the sun is at its most turbulent and violent, its surface crowded with sunspots and its atmosphere erupting frequently. Then, having reached this peak, the magnetic field does something extraordinary. It reverses. The sun's magnetic poles flip, north becoming south and south becoming north, and the field begins to unwind and rebuild in the opposite orientation. The sun then settles into a quieter period, with few sunspots and little activity, before the whole cycle begins again, building once more toward the next peak. This entire rhythm, the roughly 11-year rise and fall of solar activity, the building and reversing of the magnetic field, is the sun's magnetic heartbeat. This cycle is one of the most fundamental patterns of the sun's behavior. It means the sun is not constant in its activity, but pulses, moving between periods of calm and periods of intense magnetic fury, over and over, in a steady rhythm that has been going on for as long as the sun has existed. And every part of this heartbeat, the building of the field, the rise of activity, the reversal of the poles, the return to calm, is a product of the dynamo, driven by the sun's rotation. The differential spin winds up the field, driving the cycle forward. The rotation sets the rhythm, powers the buildup, and drives the whole magnetic heartbeat of the sun. Without the spin, there would be no dynamo to build the field, and therefore no cycle, no rhythm, no magnetic heartbeat at all. The pulse of the sun's activity is, at its root, a consequence of the sun's rotation. So the sun's spin does not just create a magnetic field. It creates a living, pulsing, cyclical magnetic field, a heartbeat that drives the rise and fall of all the sun's activity across the years. This is the deep rhythm of our star, the magnetic pulse that governs when the sun is calm and when it rages. And it is entirely dependent on the rotation we so often overlook. Now, with this understanding, we can finally appreciate the full scope of what the sun's magnetism creates, and therefore the full scope of what would be lost if the spin stopped and the magnetic heartbeat fell silent. Because the magnetic field, driven by the spinning dynamo, is responsible for an astonishing range of the sun's most dramatic and important behaviors, from the dark spots on its surface to the violent storms that can reach all the way to Earth. We have established that the sun's spin powers the dynamo, and the dynamo generates the sun's pulsing magnetic field. Now let's take stock of just how much that magnetic field is responsible for. Because when you understand the full range of what the sun's magnetism creates, you begin to grasp how much of the sun's character and how much of its influence on us depends ultimately on its rotation. The magnetic field is not a minor feature of the sun. It is the source of nearly everything dynamic and active about our star. Start with the sunspots, the very features that first revealed the sun's rotation to us. Sunspots are, at their core, a magnetic phenomenon. They are regions where the sun's magnetic field is especially intense and concentrated, so strong that it alters the local conditions and creates the dark patches we see. Without the magnetic field, there would be no sunspots at all. Then there are the solar flares, those enormous explosions on the sun's surface, the most powerful eruptions in the entire solar system. Flares are magnetic events. They occur when the sun's twisted, stressed magnetic fields suddenly snap and release their stored energy in a violent burst. No magnetic field, no flares. And there are the coronal mass ejections, the colossal clouds of charged particles that the sun hurls out into space. These, too, are driven by the sun's magnetic field, launched by the eruption and reconfiguration of magnetic structures. The great storms of the sun, the flares and the ejections that can reach across space and affect the Earth, are all magnetic in origin. The magnetic field shapes even more than this. The sun's outer atmosphere, the corona, is structured and heated by the magnetic field, its shimmering streamers and loops tracing out the magnetic architecture of the sun. The solar wind, the stream of particles flowing out from the sun, is shaped and channeled by the magnetic field as it flows into space, and the effects reach all the way to Earth. The beautiful auroras, the northern and southern lights that dance in our polar skies, are caused by charged particles from the sun, guided by magnetic fields striking our atmosphere. Even the way the sun interacts with the Earth, the space weather that can disrupt our technology, the geomagnetic storms, the whole dynamic relationship between the sun and our planet is mediated by the sun's magnetic field. In short, an enormous fraction of everything the sun does, beyond simply shining, traces back to its magnetism. And now recall the crucial fact. All of this magnetism is generated by the dynamo, which is powered by the sun's rotation. Which means that all of this, the sunspots, the flares, the ejections, the structured corona, the shaped solar wind, the auroras, the space weather, all of it depends ultimately on the sun's spin. The rotation is the root of the sun's entire dynamic personality. It is the hidden source from which all this activity flows. So when we ask what would happen if the sun stopped spinning, we are really asking what would happen if this entire cascade of magnetic activity lost its engine. And the answer is that, slowly but surely, all of it would begin to fade away. The sun would keep shining, but it would lose everything else, everything that its magnetism creates. Let's now trace exactly how that would unfold, beginning at the moment the spin stops and the dynamo loses its power. We have finally assembled the full picture. The sun's spin powers the dynamo generates the pulsing magnetic field, and the magnetic field creates the entire dynamic personality of the sun, from sunspots to flares to the space weather that reaches the Earth. So now let's imagine the moment itself. The instant the sun stops spinning. What happens to this whole magnificent engine when its driver suddenly falls still? The answer is not instantaneous, and that itself is part of what makes it so fascinating. At the very moment the sun stops spinning, nothing dramatic happens right away. The sun's magnetic field does not vanish in an instant. The sunspots do not immediately disappear. The sun, in that first moment, looks exactly as it did before, still wrapped in its existing magnetic field, still carrying whatever sunspots and magnetic structures it had at the moment of stopping. This is because the magnetic field that already exists does not depend on rotation to persist for a while. It is already there, threaded through the sun's plasma, and it will linger. What changes is not the existing field, but the ability to sustain and regenerate it. The moment the spin stops, the dynamo loses the differential rotation that winds up and amplifies the field. The engine that continuously rebuilds the magnetic field, that keeps it strong and drives its cycle, suddenly loses its power source. The dynamo, in effect, switches off. It is no longer generating new magnetic field to replace the old, and this is the beginning of the end for the sun's magnetic life. Because a magnetic field, once it is no longer being actively sustained and regenerated, will gradually decay over time. The sun's magnetic field is not permanent on its own. It requires the constant work of the dynamo to maintain it, to keep winding it up and replenishing it. Without that constant regeneration, the field begins to slowly weaken and unravel. It is a bit like a fire that is no longer being fed. The flames do not vanish the instant you stop adding fuel, but without new fuel, they gradually die down and fade away. In the same way, the sun's magnetic field, no longer fed by the rotating dynamo, would slowly begin to decay, weakening over time as the existing field dissipates and nothing rises to replace it. The moment the spin stops is the moment the fuel stops flowing to the sun's magnetic fire. So the stopping of the sun's spin does not trigger an immediate, dramatic transformation. Instead, it sets in motion a slow, inexorable decline. The dynamo switches off, and the sun's magnetic field, no longer sustained, begins its gradual decay. What follows is a slow winding down of everything the magnetic field creates, unfolding over time as the field weakens and fades. The sun would not change overnight, but it would change, steadily and profoundly, as its magnetic engine fell silent and its magnetic field slowly died away. Let's now follow that decline as it unfolds and witness the gradual transformation of our star from a dynamic, active, magnetically alive sun into something very different. And the first great change would be the disappearance of the very features that first told us the sun was spinning at all. The sunspots would begin to fade. As the sun's dynamo switches off and its magnetic field begins its slow decay, the first great visible change would unfold on the face of the sun itself. The sunspots, those dark blemishes that first revealed the sun's rotation to us, would begin to fade. And eventually, one day, the sun would produce its very last sunspot, and its face would become permanently, eerily blank. This would be the first clear sign that the sun had fundamentally changed. Remember what sunspots actually are. They are regions where the sun's magnetic field is intensely concentrated, so strong that it creates the dark patches we observe. Sunspots are a direct product of the magnetic field, and they come and go in step with the magnetic cycle, appearing in great numbers when the field is strong and active, and dwindling when the field is quiet. So as the sun's magnetic field decayed, deprived of the dynamo that sustains it, the sunspots would naturally begin to disappear. With each passing period, there would be fewer sunspots, and the ones that did appear would be weaker and smaller. The sun's face, once regularly marked by these dark blotches, would grow cleaner and smoother, the spots becoming rarer and rarer as the magnetic field that creates them faded away. And eventually, the sun would produce its final sunspot, the last one it would ever make, and then its surface would become permanently blank, a smooth, featureless disk of light, unmarked by any spot. Now here is something genuinely fascinating. We actually have a glimpse of what a sun with far fewer sunspots looks like, because it has happened temporarily in the sun's recorded history. There was a period a few centuries ago when the sun's sunspots nearly vanished for several decades, a stretch of time when astronomers looking at the sun found its face almost completely blank, with hardly any spots at all. This was a real, observed period of unusually low solar activity, a time when the sun's magnetic engine seemed to quiet down dramatically. It was temporary, and the sunspots eventually returned as the sun's activity picked back up. But it shows us that the sun can, and sometimes does, go through periods of dramatically reduced magnetic activity, its face falling nearly blank. A permanently non-spinning sun would be like this, but forever. The blank face would not be a temporary lull, but a permanent condition, the sunspots gone for good as the magnetic field faded away to nothing. The disappearance of the sunspots would be the first, most visible sign of the sun's transformation. To anyone observing the sun, the message would be clear. Something fundamental had changed. The sun's magnetic engine was winding down. Its face, once a shifting canvas of dark spots that revealed its living magnetic activity, would become a smooth, unchanging disk, placid and featureless. The last sunspot would mark the end of an era, the visible confirmation that the sun's magnetic life was fading. But the loss of the sunspots would be only the beginning, because as the magnetic field continued to decay, the sun would lose something far more dramatic than dark spots. It would lose its capacity for violence. The great storms of the sun, the flares and the eruptions, would begin to cease, and the sun would grow calm in a way it has not been for billions of years. As the sun's magnetic field continued to fade, a second, even more dramatic change would follow the disappearance of the sunspots. The sun would lose its ability to erupt. The solar flares, those explosions equivalent to billions of nuclear bombs, and the coronal mass ejections, those colossal clouds of charged particles hurled across space, would gradually cease. The most violent, powerful events in the entire solar system would simply stop happening. The sun would fall quiet, entering a calm it has not known for the whole of its long life. Recall that solar flares and coronal mass ejections are magnetic events. A solar flare occurs when the sun's twisted, stressed magnetic fields suddenly snap and release their stored energy in a violent burst. A coronal mass ejection is launched when the sun's magnetic structures erupt and reconfigure, flinging out vast quantities of material. Both of these depend entirely on the presence of a strong, active, complex magnetic field. They are, in essence, the sun's magnetic field releasing its pent-up energy in dramatic outbursts. So as the magnetic field decayed, the fuel for these eruptions would run out. With a weaker, simpler, decaying magnetic field, there would be less and less stored magnetic energy to release, and the flares and ejections would become rarer and weaker. Eventually, as the magnetic field faded toward nothing, these eruptions would cease altogether. The sun would no longer produce flares. It would no longer launch coronal mass ejections. Its capacity for violent, explosive activity would be gone, extinguished along with the magnetic field that powered it. Think about what this means. The sun, as we know it, is a violent, temperamental star, capable of unleashing the most powerful explosions in the solar system, storms that can reach across space and threaten the Earth. All of that violence, all of that explosive power comes from the magnetic field. and as the magnetic field faded, all of it would drain away. The sun would become calm, placid, quiet, no longer erupting, no longer storming, no longer capable of the dramatic outbursts that define its active character. The storms would end, and a deep calm would settle over the sun, a stillness it has not experienced in billions of years. The restless, roiling, erupting sun would become a tranquil, silent orb, shining steadily but no longer raging. There would be a strange peace to this transformation, but also a profound sense of loss, because the sun's storms, for all the danger they pose, are part of what makes it a living, dynamic star. They are the visible expression of its magnetic energy, the dramatic pulse of its activity. And as they ceased, the sun would lose that vital, dynamic character, becoming quieter and more inert. The calm after the storms would be a calm born of decline, the stillness of an engine that has run down. The sun would still shine, but it would no longer rage, its magnetic fury spent, its storms forever ended. And this loss of activity would extend even to the sun's outermost layers, to the shimmering crown of the sun that we can see during an eclipse. Because the sun's atmosphere, too, is shaped and heated by the magnetic field. And as the field decayed, even the sun's glowing crown would begin to change. As the sun's magnetic field faded, the transformation would reach even into the sun's outer atmosphere, into the shimmering halo of light that surrounds the sun and becomes visible during a total eclipse. This is the corona, the sun's crown, and it holds one of the great mysteries of solar science, a mystery whose answer means that the corona, too, depends on the sun's magnetic field. As that field decayed, the sun's crown would cool and change, and the constant wind that blows from the sun would begin to weaken. Here is the remarkable puzzle of the corona. You would expect that as you move away from the sun's hot surface, out into its atmosphere, the temperature would drop, just as the air gets colder as you move away from a fire. But the corona does the opposite. The sun's corona is astonishingly hot, far hotter than the surface below it, reaching temperatures of millions of degrees, hundreds of times hotter than the sun's visible surface. This has long puzzled scientists. How can the sun's outer atmosphere be so much hotter than the surface beneath it? What is heating the corona to such extreme temperatures? The leading answer points, once again, to the magnetic field. The sun's magnetic field is thought to be responsible for channeling energy up into the corona and heating it to those millions of degrees through various magnetic processes that transport and release energy in the sun's atmosphere. The corona is hot because the magnetic field heats it, and this means that the corona, like the sunspots and the flares, depends on the sun's magnetic field. So as the magnetic field decayed, the corona would lose its source of heating. Without the magnetic field channeling energy into it, the corona would gradually cool, its extreme temperatures dropping as the mechanism that heats it faded away. The sun's crown, that shimmering halo of superheated gas, would grow cooler and dimmer, losing the intense heat that the magnetic field provides. And this cooling of the corona would have a further consequence. The solar wind, the continuous stream of charged particles that flows outward from the sun, originates from the hot corona and is shaped and driven by the magnetic field. As the corona cooled and the magnetic field faded, the solar wind would weaken, its outward flow diminishing. The sun's constant breath of particles, blowing out across the solar system, would grow fainter and slower as the corona that produces it cooled and the magnetic field that shapes it decayed. This weakening of the solar wind is a subtle change, invisible to the eye, but it has enormous consequences that reach across the entire solar system. Because the solar wind does something vitally important. It inflates a vast, protective bubble around the whole solar system, a bubble that shields all the planets from the harsh environment of interstellar space. As the solar wind weakened, that protective bubble would begin to shrink. And this is where the effects of the sun stopping would reach all the way out to the edges of the solar system and back to the Earth in ways that are genuinely significant. The cooling of the sun's crown and the weakening of its wind would set in motion changes far beyond the sun itself. But before we follow those changes out into the solar system, let's pause to picture what the sun itself would have become. Because by this point, our star would have transformed into something profoundly different from the sun we know. Let's step back and picture the sun as it would be after its magnetic field had fully decayed, after the dynamo had been silent for a long time, and the magnetic engine had wound down completely. What we would be left with is a star profoundly transformed, not in its brightness or its gravity, but in its entire character. The sun would have become, in a sense, a star with no personality, a quiet, placid, featureless orb, stripped of everything that made it dynamic and alive. Picture it. The sun's face would be permanently blank, smooth and unmarked, with no sunspots ever appearing to break its featureless surface. There would be no flares erupting from it, no coronal mass ejections blasting out into space, no violent storms of any kind. Its corona would be cooler and dimmer, no longer the shimmering, superheated crown it once was. Its solar wind would be weak and faint, a shadow of the vigorous stream it used to blow. The sun would simply shine, steadily and quietly, a smooth ball of light pouring out its energy without any of the dynamic activity that once defined it. Gone would be the magnetic heartbeat, the cycle of activity, the rise and fall of storms. Gone would be the restless, roiling, erupting character of our star. In its place would be a calm, inert, unchanging sun, still shining as brightly as ever, but utterly quiet, utterly still, its magnetic soul faded away to nothing. There is something almost haunting about this image. The sun we know is a living, dynamic star, its surface constantly changing, its magnetic activity rising and falling, its storms erupting and its face shifting from day to day. It is a restless, energetic, sometimes violent object, full of drama and motion. And all of that character, all of that dynamism, comes from its magnetic field, which comes from its spin. Take away the spin, and over time you take away the personality. What remains is a sun that shines but does not live in the same way, a star reduced to its most basic function, giving light and heat, but stripped of the rich, dynamic magnetic behavior that makes it such a fascinating and formidable object. It would be like the difference between a roaring, crackling fire and a steady, silent glow. The light and warmth remain, but the life, the movement, the drama, would be gone. And remember, this would not be a temporary lull, like the historical periods when the sun's activity dropped for a few decades. It would be permanent. Without its spin, the sun would have lost its magnetic engine for good, and there would be no coming back, no return of the sunspots and the storms, no revival of the magnetic heartbeat. The sun would remain a quiet, placid, magnetically dead star indefinitely, shining on in silence. This is the ultimate fate of a sun that stops spinning, not a dramatic explosion or a sudden darkening, but a slow fading of its dynamic soul, leaving behind a beautiful but lifeless glow. And yet, the story does not end at the sun itself. Because the changes we have described, especially the weakening of the solar wind, would ripple outward across the entire solar system, reshaping the vast protective bubble that surrounds us all. Let's follow those ripples outward now, to the very edge of the sun's domain. The transformation of the sun would not stay confined to the sun itself. Through the weakening of the solar wind, the effects would reach outward across the entire solar system, all the way to its distant edge, reshaping a vast, invisible structure that surrounds and protects every planet, including our own. This structure is called the heliosphere, and understanding what would happen to it reveals how the sun stopping would affect the whole solar system, not just the sun. The heliosphere is an enormous bubble, inflated and maintained by the solar wind. As the sun blows out its constant stream of charged particles, that solar wind pushes outward in all directions, carving out a vast region of space that extends far beyond the orbits of all the planets, out to distances many times farther than the most distant planet. This immense bubble, filled with the solar wind and dominated by the sun's influence, is the heliosphere. It represents the sun's domain, the region of space where the solar wind holds sway, and it is surrounded on the outside by the interstellar medium, the thin gas and particles that fill the space between the stars. The heliosphere is, in effect, the boundary between the sun's realm and the wider galaxy, a bubble blown by the solar wind that pushes back against the pressure of interstellar space. Its size depends on the strength of the solar wind. A strong solar wind inflates a large heliosphere, pushing the boundary far out. A weaker solar wind cannot push as hard, and the boundary contracts inward. So as the sun's solar wind weakened, deprived of the magnetic field and the hot corona that drive it, the heliosphere would begin to shrink. With less pressure pushing outward, the boundary of the sun's domain would contract, pulling inward as the weakening solar wind lost its ability to hold back the surrounding interstellar medium. The vast bubble that the sun blows around the solar system would deflate, shrinking down as the wind that inflates it faded. The sun's realm would contract, its influence pulling back toward the inner solar system as the heliosphere collapsed inward. Over time, as the solar wind grew fainter and fainter, the heliosphere would become smaller and smaller, a diminishing bubble around a sun whose magnetic engine had fallen silent. This shrinking of the heliosphere matters because the heliosphere is not just an empty boundary. It is a shield. It helps protect the solar system, including the Earth, from some of the harsh radiation that fills interstellar space, particularly the high-energy particles known as galactic cosmic rays that stream through the galaxy. The heliosphere, inflated by the solar wind, helps to deflect and reduce the amount of this galactic radiation that penetrates into the inner solar system. So as the heliosphere shrank, its protective power would weaken, allowing more of this harsh galactic radiation to reach the inner solar system and the planets within it. This is one of the most significant ways the sun stopping would affect the Earth, not through any change in the sun's light, but through the weakening of the invisible shield that the solar wind provides. And this brings us to the surprising balance of consequences for the Earth, because the sun stopping would bring both good news and bad news for our planet, and the good news comes first. Now let's bring the consequences of the sun stopping home to the Earth and consider what it would actually mean for our planet. And here we find a genuinely surprising twist. Because in some important ways, a sun that stopped spinning and lost its magnetic activity would actually be a safer, gentler neighbor for the Earth. There would be real benefits to living beside a quiet, magnetically dead sun. Let's start with this good news, because it is the more unexpected side of the story. Recall all the ways the sun's magnetic activity threatens the Earth. The solar flares, unleashing bursts of radiation that can disrupt our communications and satellites. The coronal mass ejections, hurling clouds of charged particles at the Earth, triggering geomagnetic storms that can damage power grids, knock out satellites, and disrupt the technology our civilization depends on. We have discussed how a powerful enough solar storm could potentially cause catastrophic damage to our modern, technology-dependent world, collapsing power grids across entire continents and causing damage taking years to repair. All of this danger, all of this threat from space weather, comes from the sun's magnetic activity, from the flares and the eruptions driven by the magnetic field. And as we have seen, if the sun stopped spinning, that magnetic activity would fade away, and the flares and eruptions would cease. So here is the good news. A sun that stopped spinning would, over time, stop threatening the Earth with solar storms. No more flares to disrupt our radio communications. No more coronal mass ejections to trigger dangerous geomagnetic storms. No more risk of a catastrophic space weather event collapsing our power grids or destroying our satellites. The single greatest threat the sun poses to our technological civilization, the danger of a massive solar storm, would gradually disappear as the sun's magnetic engine wound down. Our satellites would be safer. Our power grids would be safer. Our astronauts would face less danger from solar radiation. In terms of space weather, a quiet, non-spinning sun would be a far gentler and safer neighbor than the active, storming sun we know. The looming threat of a devastating solar storm, which hangs over our modern world, would simply fade away. There is a real irony here. We have spent much of this exploration mourning the loss of the sun's dynamic magnetic activity, its sunspots and storms and magnetic heartbeat. But that same activity is precisely what threatens our technology and our infrastructure. So its loss, while it would rob the sun of its dynamic character, would also remove one of the most significant natural dangers our civilization faces. A non-spinning sun would be less interesting, less dynamic, less alive in its magnetic behavior. But it would also be less dangerous, sparing us the threat of the catastrophic solar storms that could one day cripple our technological world. This is the unexpected upside of the sun stopping, a genuine benefit hidden within the transformation. But it is not the whole story. Because the shrinking of the sun's protective bubble would bring a downside as well, a new danger to balance against the loss of the solar storms. And this is the bad news for the Earth. We have seen the surprising upside of a non-spinning sun, the end of the dangerous solar storms that threaten our technology. But there is a downside to balance against it, a new danger that would emerge as the sun's protective influence faded. Because while the loss of the sun's magnetic activity would spare us from solar storms, the shrinking of the sun's protective bubble would expose the Earth to a different kind of threat, one that comes not from the sun, but from the wider galaxy beyond. Recall what happens to the heliosphere when the solar wind weakens. That vast protective bubble, inflated by the solar wind, shrinks and contracts, losing its ability to hold back the harsh environment of interstellar space. And one of the most important things the heliosphere holds back is galactic cosmic radiation, the stream of extremely high-energy particles that races through the galaxy, produced by violent events like exploding stars far across the cosmos. These galactic cosmic rays are constantly bombarding the boundary of the solar system, and the heliosphere, inflated by the solar wind, helps to deflect and reduce the amount of this radiation that penetrates into the inner solar system. So, as the heliosphere shrank, more of this galactic cosmic radiation would make its way into the inner solar system, reaching the region where the Earth orbits. The weakening of the sun's protective bubble would let in more of the harsh radiation from deep space, increasing the amount of galactic cosmic radiation that reaches our vicinity. Now, it is important to keep this in perspective, because the Earth has its own defenses beyond the heliosphere. Our planet has its own magnetic field and its thick atmosphere, which together provide significant protection against radiation, shielding the surface even if more cosmic rays reach the vicinity of the Earth. So life on the surface would still be substantially protected by the Earth's own defenses. But the increased galactic radiation would still have consequences. It would pose a greater hazard to astronauts in space, to high-altitude aircraft, and to satellites, all of which rely partly on the heliosphere's protection and would face more radiation without it. There could also be subtle effects on the Earth's atmosphere and environment from the increased radiation reaching us. In short, the shrinking of the Sun's protective bubble would expose the Earth and the solar system to more of the harsh radiation of interstellar space, a real downside to set against the loss of the solar storms. So the consequences for the Earth would be a genuine trade-off, a balance of good and bad. On one hand, we would be freed from the threat of catastrophic solar storms, our technology safer from the flares and eruptions of an active sun. On the other hand, we would lose some of the protection the solar wind provides against galactic radiation, as the heliosphere shrank and let more cosmic rays into the inner solar system. It is a fascinating illustration of how deeply the sun's activity is woven into the environment of the entire solar system. The sun's magnetic storms are both a threat and a shield, dangerous in their direct effects, but protective in the bubble they help maintain. Remove them, and you gain safety from one danger while losing protection against another. But beyond these practical consequences, there is one more change that a non-spinning sun would bring to the Earth, a change that is less about danger and more about beauty. Because the quiet sun would also transform the very sky above us, dimming one of nature's most spectacular displays. Beyond the practical trade-offs of danger and protection, a sun that stopped spinning would change something more visible and more beautiful. It would transform the sky above the Earth, dimming and eventually erasing one of the most spectacular natural displays our planet has to offer. Because the auroras, the shimmering northern and southern lights that dance in the polar skies, depend on the sun's magnetic activity. And as that activity faded, so too would these breathtaking lights. Consider what causes the auroras. Those glowing curtains of green and red and purple light that ripple across the polar skies are produced when charged particles from the sun, carried by the solar wind and especially by solar storms, strike the Earth's atmosphere. Guided by the Earth's magnetic field toward the polar regions, these particles collide with the gases in our upper atmosphere and cause them to glow, painting the sky with shimmering, dancing light. The auroras are, in a very real sense, a gift from the sun's activity, a visible product of the interaction between the sun's charged particles and the Earth's magnetic field. The more active the sun, the more intense and widespread the auroras, with the greatest displays often triggered by powerful solar storms that send extra waves of particles toward the Earth. So the auroras are intimately tied to the sun's magnetic behavior, to the solar wind and the storms that a spinning sun produces. So as the sun's magnetic activity faded and its solar wind weakened, the auroras would begin to dim. With fewer charged particles streaming from the sun, and no more solar storms to send extra waves of them toward the Earth, the auroras would grow fainter and rarer. The spectacular displays triggered by solar storms would cease, since the storms themselves would have ended. And as the solar wind weakened to a faint trickle, even the ordinary quieter auroras would fade. Eventually, the northern and southern lights, one of the most beautiful natural phenomena on Earth, would largely disappear from our skies, dimmed and erased along with the solar activity that creates them. The polar skies, once alight with dancing color, would grow dark and still. The auroras faded into memory. A quiet sun would mean a quieter, darker sky, stripped of one of its most magnificent displays. There is a poignancy to this. The auroras are one of the ways we directly experience the sun's dynamic activity here on Earth, a visible, beautiful connection between our planet and the living, magnetic sun. And they, too, would be lost if the sun stopped spinning, another casualty of the fading magnetic field. The sky above us would be subtly but genuinely different, missing the shimmering lights that have inspired wonder in humans for as long as we have existed. It is a small change compared to the collapse of power grids or the shrinking of the heliosphere, but it is a deeply felt one, a loss of beauty to accompany the loss of the sun's dynamic character. And it points to the profound truth at the heart of this entire exploration, that a single, invisible motion, the quiet spinning of the sun, secretly touches almost everything, from the storms that threaten our technology to the lights that dance in our skies. Let's reflect now on just how remarkable that truth really is. We have traced the astonishing cascade of consequences that would follow if the sun stopped spinning. And now, it is worth pausing to absorb the deeper lesson hidden in all of it. Because what this entire journey reveals is something genuinely profound. A single, quiet, invisible motion, the spinning of the sun, a motion we almost never think about, is secretly the engine behind an enormous fraction of everything the sun does, and its influence reaches across the entire solar system. The spin runs almost everything, and yet we hardly ever notice it is there. Think back over everything we have discovered. The sun's spin, through the dynamo, generates its magnetic field. That magnetic field creates the sunspots, drives the flares and the coronal mass ejections, structures the corona, shapes and powers the solar wind, and sets the rhythm of the 11-year magnetic cycle. The solar wind inflates the vast heliosphere that surrounds and protects the entire solar system. The sun's charged particles paint the auroras across the Earth's skies. The sun's storms threaten our technology, and its protective bubble shields us from galactic radiation. Every one of these phenomena, spanning from the surface of the sun to the distant edge of the solar system to the skies above the Earth, traces back, ultimately, to the quiet spinning of our star. The rotation is the hidden root from which this entire vast tree of consequences grows. It is, in a very real sense, the motion that runs everything about the sun's dynamic character and its influence on its surroundings. And here is what makes this so striking. The sun's spin is completely invisible to us in our daily lives. We never see it, never feel it, never think about it. The sun appears to us as a steady, unchanging light in the sky, and its slow rotation, taking about a month to complete, is utterly imperceptible without careful observation. And yet, this overlooked, invisible motion is quietly powering a cascade of phenomena so vast that it shapes the environment of the entire solar system. It is a perfect illustration of how the universe works, how a simple, hidden process can be the source of enormous complexity and activity, how the things we overlook can be the very things that matter most. The sun's spin is a quiet engine, running silently in the background, and almost everything dynamic about our star depends upon it. Take it away, and the whole magnificent edifice of solar activity slowly crumbles. This is perhaps the most beautiful and humbling insight of our entire exploration, that the restless, storming, dynamic sun, with all its magnetic fury and all its far-reaching influence, ultimately owes its character to nothing more than a gentle, invisible spin, a motion inherited from the cloud it was born from, billions of years ago. The spin is the sun's secret heartbeat, the hidden source of its life and its power, and it reminds us that in the universe the deepest causes are often the quietest, the most overlooked, the most easily taken for granted. But this raises one final, fascinating question, the the question we have been holding in reserve. Could the sun actually stop spinning? Is this scenario a real possibility or purely a thought experiment? And the answer, it turns out, connects our imaginary scenario to something real that is happening to the sun right now, very slowly, across the vast reaches of cosmic time. Throughout this exploration, we have imagined the sun suddenly stopping its spin and traced the profound consequences that would follow. But we should be honest about the nature of this scenario. Could the sun actually stop spinning all at once the way we have imagined? And the answer is no, not suddenly. But the deeper truth is far more fascinating because in a slow, gentle way, the sun really is winding down its spin and has been for its entire life. First, why the sun cannot simply stop spinning all at once. There is a fundamental principle of physics, the conservation of angular momentum, which says that the spin of an object cannot simply vanish into nothing. The sun's rotation represents an enormous amount of angular momentum, and that angular momentum has to go somewhere. It cannot just disappear. For the sun to suddenly stop spinning, all that angular momentum would have to be instantly transferred elsewhere, which is not something that can happen naturally. So the scenario of the sun abruptly halting its spin is indeed a thought experiment, a way of exploring the deep importance of the sun's rotation, rather than a literal event that could occur overnight. The sudden stop is imaginary, a tool for understanding just how much depends on the spin. But here is the remarkable real truth. The sun is, in fact, gradually slowing down its rotation over immense stretches of time, and the mechanism is beautifully connected to everything we have discussed. As the sun blows out its solar wind, that magnetized wind carries away a tiny bit of the sun's angular momentum with it. The charged particles streaming out from the sun, flung outward along the magnetic field lines, act like a gentle brake, very slowly bleeding away the sun's rotational momentum over time. This process, called magnetic braking, means that the sun's spin is gradually slowing as it ages, decade by decade, eon by eon. The sun was actually spinning considerably faster when it was young, and it has been slowing down ever since, braked by its own magnetic wind. In fact, this effect is so reliable that astronomers can estimate the age of sun-like stars by measuring how fast they spin, because these stars slow down predictably as they grow older. The faster a sun-like star spins, the younger it tends to be, and the slower it spins, the older it is. Do you see the beautiful connection? The sun's spin drives its magnetic field. Its magnetic field drives its solar wind, and its solar wind slowly breaks its spin. It is a great, slow feedback loop playing out over billions of years, gradually winding down the sun's rotation. And this means that, in a very real and gentle way, the sun is slowly heading toward the quieter, less active state we have been imagining. Not suddenly, not overnight, but across cosmic time, the sun is gradually slowing its spin, and as it does, its magnetic activity will very slowly decline over the ages. Our imaginary scenario of a sun that stops spinning is, in truth, just the far distant direction in which the sun is already, ever so slowly, traveling. The sudden stop is imaginary, but the gradual slowing is real, an actual process unfolding right now, so gently that it takes billions of years to make a difference. The sun is winding down, one faint breath of solar wind at a time. So the next time you look up at the sun carefully and see that steady, unchanging light in the sky, remember the hidden motion within it. The sun is spinning, silently, slowly, turning on its axis as it has since the day it was born from a collapsing cloud billions of years ago. You cannot see that spin, you cannot feel it, it makes no sound and gives no sign, And yet within that silent turning lies the secret engine of the sun's entire dynamic soul. We began tonight with a simple question. What would happen if the sun stopped spinning? And the answer turned out to be far stranger and more beautiful than anyone might have guessed. The sun would not go dark. It would not lose its gravity. It would not change its shape. On the surface, it would seem as though nothing had happened at all. But hidden beneath that calm, the sun would be transformed. Its magnetic engine would fall silent. Its sunspots would fade. Its storms would cease. Its corona would cool, its wind would weaken, and the vast protective bubble around the entire solar system would slowly shrink. The auroras would fade from our skies. The sun would become a quiet, placid, magnetically dead star, still shining, but stripped of the restless, magnetic life that once defined it. And all of this entire cascade of transformation reaching from the surface of the sun to the distant edge of the solar system, would flow from the loss of a single, quiet, invisible spin. There is a profound lesson in this, one that reaches beyond the sun itself. It is a reminder that in the universe, the deepest and most powerful causes are often the quietest and the most overlooked. We tend to notice the dramatic things, the storms and the eruptions and the bright displays. But behind them so often lies something simple and silent, a hidden motion, a quiet process, an invisible engine that we never think to consider. The sun's spin is exactly such a thing. Unseen, unfelt, taken utterly for granted, and yet the secret source of nearly everything dynamic about our star. To understand the sun fully is to appreciate not just its brilliant light and its immense power, but its quiet, hidden spin, the gentle turning that runs it all. And perhaps that is the most fitting note to end on. Because even now, as you read this, the sun is turning, silently and slowly, its equator lapping its poles, its magnetic field winding up in the depths, its storms brewing and its wind blowing out across the solar system. And ever so gradually, across the vast reaches of time, that spin is slowing, winding down by the faintest degree with every passing age, carrying the sun over billions of years toward a quieter and calmer future. The sun we know, restless and storming and alive, is a passing phase in the long life of a slowly spinning star. It will not last forever. Nothing does. But for now, in our brief moment, the sun turns and storms and shines, and paints our skies with light, all because of a silent motion set in place at the dawn of the solar system. Look up, and though you cannot see it, know that it is there. The silent turning of the sun, the quiet engine of our star, spinning on as it has for billions of years, and as it will for billions more.